Hi everybody, today I will talk about Michaelis-Menten pharmacokinetics, a basic review. For today's lecture, we will have two parts. Part 1, about 30 minutes with me. I will teach you about the basic review in nonlinear kinetics following Michaelis-Menten. And the rest of time, Dr. Titus Lay will teach you about clinical application. My lecture is based on the reference book Applied Clinical Pharmacokinetics, the third edition. This one is available at Access Pharmacy. After my lecture, you should be able to describe Michaelis-Menten pharmacokinetics or saturable pharmacokinetics and its contents values. Explain why some drug, such as Phenytoin, follows the Michaelis-Menten pharmacokinetics. Describe important pharmacokinetics parameters such as volume distribution, clearance, and half-life in Michaelis-Menten pharmacokinetics. And last but not least, calculate the doses for drugs, example with Phenytoin, following the Michaelis-Menten pharmacokinetics. This is a basic profile of a drug expressing the relationship between the dose and the steady-state concentration. Normally, when the dose increases, the steady-state concentration will increase, and if the increasing proportionally with the dose, we have a linear line like this. And if the drug follow the linear lines when the dose increase and the steady-state concentration increase proportionally with the dose, we call linear pharmacokinetics or first-order kinetics. However, for some drugs, at certain points when the dose increase, the concentration increase but below expectation. That's we call saturable protein binding or autoinduction. These are different nonlinear pharmacokinetics. Another situation, at certain point of the dose, when the dose increase, the steady-state concentration increase more than expected, like this. And in this case, we call Michaelis-Menten pharmacokinetics. So for Michaelis-Menten pharmacokinetics, when the dose increase, the steady-state concentration increase disproportionately with the dose, and the increasing will be more than expected. So why this happen? This happen with some drugs, but not with many drugs. Most of drugs follow linear pharmacokinetics. For some drug, for example, Phenytoin, when the dose increase, the drug will be increased sharply like this. The reason is that the drug is highly metabolized by the cytochrome P450 enzyme or other enzyme system. The drug is highly metabolized by the enzyme. However, when the dose increases to certain level, for example in this level, the capacity of enzyme is limited, and when the dose increases like this, they don't have any enzyme to metabolize the drug. In this case, we call enzyme saturation or saturable enzyme. So no more enzyme to metabolize the drug. So the drug or the pure drug will appear in the blood more. That's why we call this Michaelis-Menten pharmacokinetics and also the saturable pharmacokinetics. In the Michaelis-Menten pharmacokinetics, the calculation and equation will be different. Remember, we have three important parameters we need to know. That's volume distribution, clearance, and half-life, right? We learned about linear pharmacokinetics. So what happened to the three parameters values in Michaelis-Menten? In Michaelis-Menten, there's two important constants. The calculation is not straightforward like linear pharmacokinetics is different, and it much depends on the two Michaelis-Menten constant. Before we go to the value, let me show you the graph here. The graph here expresses the relationship between drug concentration and the rate of metabolism. When the drug concentration increase, the rate of metabolism increase. But at a certain point, when the capacity of enzyme is saturated, right? So the rate will be increased, but it's not proportional with the dose. And at a certain point, when the maximum capacity of enzyme is reached, that means no more enzyme or no more metabolism. And at this point, we call the value of metabolism rate, we call Vmax. Vmax, that is the maximum rate of metabolism. And the Vmax here will be correlate with certain dose. Like with certain dose, the drug concentration or the drug metabolism will reach maximum. That means after this point, no more metabolism. And after this point, usually the drug will be like concentration in the blood will be increased sharply. So we have the Vmax. And it's at this point we call 100% of metabolism. The second constant value in Michaelis-Menten PK is the Km. When the Vmax, when you look at the value of Vmax when it's about 50% of metabolism, this means about capacity about 50%. So, and you point it here to find the concentration. The concentration of the drug that the metabolism rate reach a half of Vmax, we call Km. So these are the two important values in Michaelis-Menten when you want to calculate the dose. So again, Vmax is the maximum rate of metabolism, and correlate with the Vmax, there will be certain dose to get the Vmax. And Km is the value of the drug concentration where Vmax reach a half. So for this Vmax and Km, where can you get that value? Vmax and Km are obtained from a lot of study from the population for certain drug, and they will have the average Vmax and average Km based on the population. So from Vmax and Km population, you can calculate the dose for individual, and then you monitor the dose, and you can come back and change like needed. So we know that for clinical pharmacokinetics, three important values we need to know. They are clearance, volume distribution, and half-life. We learned already on linear PK, clearance is a constant value. It doesn't change, right? But in Michaelis-Menten PK, it's very different. Clearance in Michaelis-Menten PKs is concentration dependent or dose dependent. That means the clearance value is dependent on the concentration of the dose. When the concentration or dose increase, the clearance will be decreased. The formula to calculate clearance for Michaelis-Menten PKs is Vmax divided by Km plus C. From this equation, you can see the trend easily. C, the value here is a steady state concentration. Whenever you want to change the C, like you want to increase the C's. When you increase the C, the whole denominator value here will be increased, right? When it's increased, the ratio of Vmax divided by this Km plus C here will be decreased. So that's make the whole value clearance decrease. So in short, for Michaelis-Menten PK, the clearance is not constant. It depends on concentration or depends on the dose. And when the concentration increase, the clearance value will be decreased. The next value in PK value, we need to know volume distribution. Volume distribution, usually volume distribution is calculated based on the initial concentration and the dose, right? So the concentration initial, when you know the concentration of the dose, then you can calculate the volume distribution. And it's like linear pharmacokinetics. A volume distribution for Michaelis-Menten is not affected by saturable metabolism. It's still like be determined by the volume of blood and tissue as linear pharmacokinetics. So volume distribution won't change when the dose increase in Michaelis-Menten PK. How about half-life? Remember, in linear pharmacokinetic, half-life is constant, and usually half-life is calculated based on the rate constant, right? Half-life equals 0.693 divided by K. In this here, you cannot use that equation anymore because half-life in Michaelis-Menten is not constant. Another equation to see the relationship between half-life and clearance. So half-life equal to 0.693 times volume distribution and divided by clearance. If you look at this, the clearance, when the dose increase, the clearance increase or decrease? When the dose increase, the clearance decrease. So when the clearance decrease, from the formula you see that denominator decrease, the half-life will increase. It makes sense because the clearance, when the clearance decrease, like the removal of the drug from the body decrease, so more drug or the drug will stay longer in the body. So that's why half-life will be longer. Again, for Michaelis-Menten PK, when the dose increase, the volume distribution doesn't change, but clearance will be decreased and half-life will be increased. Half-life and clearance for Michaelis-Menten PK are not constant. So when the half-life increase like that, how about the time to reach the steady state? The time to reach steady state still around 3 to 5 half-life. So when the half-life increase, of course, 3 to 5 half-life will be longer than the dose in the linear kinetics. Now we go to the calculation for loading dose and maintenance dose for the drugs following Michaelis-Menten PK. The loading dose, remember in linear PK, loading dose equal to volume distribution times CSS, because for Michaelis-Menten PK, volume distribution doesn't change. So you still can use the same equation for linear kinetics to calculate loading dose for the drug following Michaelis-Menten PK. For the maintenance dose, the equation is a little bit different, but it still follows the same concept. Remember, in linear pharmacokinetics, maintenance dose equal to clearance times CSS. For Michaelis-Menten PK, the maintenance dose is still calculated equal to clearance times CSS. It's different. It's just different because clearance in Michaelis-Menten PK is different. So for the Michaelis-Menten PK, clearance equal to Vmax divided by Km plus CSS. So when you plug in the equation, maintenance dose equal to clearance times CSS, you will have Vmax times CSS divided by Km plus CSS. The section of Vmax divided by Km plus CSS equal to clearance. So when you know the population value of Vmax Km and when you know your desirable concentration at steady state, then you can calculate the maintenance dose. Okay, to clarify the concept we just learned, now we go with some calculation example. For example, you know that the average value of Michaelis-Menten pharmacokinetics parameter for phenytoin in a dose of Vmax equal 500 mg per day and Km equal to 4 mg per liter. What are the expected dosage of phenytoin that would produce steady-state concentration at the lower and upper limits of the therapeutic range? And you know that the therapeutic range will be 10 to 20 mg per liter. So what's information we have here? Provided you have the Vmax equal 500 mg per day and Km equal to 4 mg per liter. Usually these parameter or these values are obtained from literature search. So for phenytoin, if for the dose, if you put the dose 500 mg per day, it will reach the maximum metabolism, and above this dose, the drug will not be metabolized, and the concentration can increase sharply, and it can be associated with toxic. Km equal to 4 mg per liter. That means at this concentration, the Vmax will will be a half of Vmax will be obtained. And the therapeutic range is from literature search to 10 to 20 milligram per liter is the therapeutic range for phenytoin. So how to calculate the dose? We know that a phenytoin follows the saturable pK or Michaelis-Menten pK, so we can use the equation applied for Michaelis-Menten pK. Maintenance dose equal to clearance times CSS or equal to Vmax divided by Km plus CSS times CSS. So this the equation we will apply. If you want the steady state concentration or the desirable concentration at 10 milligram per liter, if you want that the concentration of CSS, you plug the number 10 here for CSS. Vmax and Km, you have the volume, the values from here. So plug the number in, algebraic calculation. For CSS equal to 10 milligram per liter, you will have maintenance dose calculated to be 357 milligram per day. In case you want to increase the steady state concentration to 20 milligram per liter, you will replace CSS here by 20 milligram per liter. Vmax and Km are the same value here. Plug the number in, algebraic calculation, maintenance dose is calculated to be 470 milligram per day. So to reach the steady state or to reach the therapeutic window of concentration between 10 to 20 milligram per liter, the dose should be at 357 milligram per day to 417 milligram per day. Based on this calculation, if the dose below 357 milligram per day, the concentration obtained may be below the MEC. However, when the dose increases more than 417 milligram per day, the obtained concentration may be above MTC. In this calculation here from my example, I just give you the accurate exact calculation. In practice, the dose can be routed, technically will be routed practically to make sure that it can be feasible based on the dosage form, based on the dose, or it can be the routing can be different from this number in practice use. Okay, now we go to the second question. In this question, phenytoin follows Saturo pharmacokinetics with average Michaelis-Menten constant of Vmax equal to 500 milligram per day and Km equal to 4 milligram per liter. And again, you know that therapeutic range of phenytoin is at 10 to 20 milligram per liter. The question is that when the steady state concentration of phenytoin increases from 10 to 20 milligram per liter, what is the change in clearance? The question asks you if you increase the dose. So to get the steady state concentration increasing, what happened to clearance? Remember, we just learned in a concept in Michaelis-Menten pK. When the dose increases, the clearance will decrease. So let's use calculation to clarify or to prove the concept. The calculation from Michaelis-Menten pK, we use the equation clearance equal to Vmax divided by Km plus C. And if the steady state concentration we use 10 milligram per liter, what's the clearance? You can plug in Vmax and Km from the population number you have here, and C is the concentration you want to reach. Then algebraic calculation, clearance equal to 36 liter per day. That's a volume. That's a value of clearance when you want the patient concentration at 10 milligram per liter. If you want to increase the concentration at steady state to 20 milligram per liter, how to calculate clearance? You use the same equation, but then you change the C to the new value here, 20 milligram per liter. Km and Vmax still the same. Algebraic calculation, clearance equal to 21 liter per day. So clearly you see when the dose increased from 10 milligram per liter to 20 milligram per liter, the clearance will be decreased from 36 liter per day to 21 liter per day. So this proves the concept we should learn. And there's something you need to know, that the value of Vmax we have here is the average on the population. Actually, the Vmax for phenytoin, it can be different from patient to patient, and the Vmax can be from 100 to 1000 milligram per day. And the Km value for each patient can range from 1 to 10 milligram per liter. So in this case, you see the Vmax changed a lot and the Km changed a lot. If we dose the patient and we use the average one, some patient with the low value Vmax and Km or very high Vmax and Km, the dose with the dose we provide, we may not reach the expected steady state concentration. So we can say that dosing the drug follow Michaelis-Menten PK or Saddle PK is very, very difficult, because for some patient, when you give the average dose based on the population, it can be below MEC. But for some patient with the same thing like that, when you dose like that, but it can be above MTC. So usually for this kind of drug, there should be very close monitoring. Okay, we go to the next question. TD is a 32 years old, 70 kilogram male with generalized tonic-clonic seizures. Assuming Michaelis-Menten parameters of Vmax 500 mg per day and Km equal 4 mg per liter, calculate a dose of phenytoin that will achieve CSS equal to 50 mg per liter. Remember, we assume, like from the literature, the therapeutic window for CSS of phenytoin is 10 to 20 milligram liter. So now you don't want to reach minimum or maximum, you want in the middle, and you want the CSS of the patient is 50 milligram per liter to ensure the treatment. So in this case, how can you calculate the dose? So for the dose, we use the same equation. A maintenance dose for Michaelis-Menten PK equal to Vmax times CSS divided by Km plus CSS. Then you just put the CSS 15 milligram per liter in this equation, plug the number in, Vmax and Km you have from here. So just put the number in, algebra calculation, you have maintenance dose for this patient will be 350 milligram per day based on accurate calculation. And of course, in practice, clinically, you can route the dose